Hello and welcome to another session of Introduction to Astrophysical Fluids. In this session, we will discuss the concept of plasma. Basically, it will be an introductory session. I somehow assume that you know either very few about plasma or maybe nothing about plasma. Okay, so I will start by giving a very basic knowledge of plasma, and then I will try to cover several aspects which are relevant for our course. Okay, so it is true that almost 70% of the course till now, so 70% of the whole course which is done till now, we have only discussed about neutral hydrodynamic fluids, and we discussed various astrophysical phenomena just using neutral fluids. Although in some cases we said that the consideration of the plasma aspect and at least the magnetic field is very necessary, but we have not treated anything other than neutral fluid till now. Okay. Now, in reality, as we know, that almost all the astrophysical media belongs to the class plasma. And then the natural question, of course, comes that what is a plasma? How can we characterize a plasma? How can a plasma be sufficient or be useful in explaining several astrophysical phenomena? Okay, and can we derive the same type of fluid equations for plasma? Okay, so and can we also have the same type of properties as we have discussed for normal fluids? Can we also have this type of fluid properties in case of a plasma fluid? That we will try to discuss in this course. But specifically in this lecture, I will mainly give you a very basic introductory view of plasma. So the first question which comes to our mind is, what is a plasma? And of course, the first thing which comes to our mind from our general knowledge is that plasma is nothing but the fourth state of matter. So when we were in high schools, okay, suddenly maybe during some quiz competition or some TV program of general knowledge or by some science teacher, we came to know that, well, besides solid, liquid and gas, there exists another state of matter which is plasma. Now this is very, very true, and even at this level we will not change we will not really change this concept. This concept is completely right. That is, plasma is exactly the fourth state of matter, but this is not something very, very much mysterious, because from my personal experience, I saw that whenever we are talking about solids, liquids and gas, people are very energetic in discussing. Once I just entered in the plasma, they say, well, oh my god, this is something, oh, it's too much, it's enigmatic, it's mysterious. So the first comment is that plasma is not a mysterious thing. It's a very, very interesting thing. If you know classical mechanics and electrodynamics, then you can gain sufficient knowledge about normal or usual plasma. Okay. So as you can see in this picture, that solid to liquid to gas to plasma is just a transformation which is classified by an increase in the energy. Okay, so if you give some energy, for example, if you heat a solid, it will melt. If you further heat the liquid, it will vaporize. Now when you further continue heating this gas, what happens? Well, the gas molecules or atoms will now get ionized, and the gas which was previously just an ensemble of neutral molecules or neutral particles will now be a collection of some positive charges and some negative charges. That means the ions and the electrons. Okay. This is the, very common case of a plasma. There can be a bit more complicated plasma which can also contain, okay, more than one type of positive ion, more than one type of negative ions. Okay, so a general plasma can contain one or more type of positive ions, okay, electrons, maybe some negative ions, and also do not forget that a plasma is almost never 100% ionized. So there should always be some neutral particles intact. So a plasma as a whole is the gas which contains three type of particles. One is positive ions or negative ions. Not or, but sometimes and sometimes negative ions. Number two, electrons. Number three, neutrals. Okay. So you can simply understand that a plasma is a collection of all this. Okay. Now, in various cases, under various circumstances, you will see that for the sake of simplicity, people just consider a plasma which is fully ionized and just is a collection of only positive and negative ions. But this is not the real case, although for some analytical convenience we do that. Okay. Now try to understand that you have heated the system gets ionized. Okay. So the system now has a lot of energy. Okay. So when the system was just neutral gas type of thing, okay, so with respect to that state, now the system has much more energy. Okay, so this energy, a part of this energy is used as the ionization energy of this molecules. Okay, energy of ionization. Now the rest of the energy supplies, energy supplies the kinetic energy of this charged particles. So a plasma is a collection of charged particles and eventually neutrals neutral particles which move in the system, right? Okay, now you can easily understand that when this system was simply just an an ensemble of neutral molecules or atoms, okay, then if you just put an electric field like this, plus minus, okay, then my question is that would that be affected? Well, the answer is yes, but at least what happens that there can be some polarization in this molecules or atoms, okay, but so I mean that depends on the particles, of course, okay. Now in general the system is not ionized, but let's say that you are making the gas very dilute. So you are making the gas very rarefied. Okay, the density is very low, density low, and you are not heating the system, but you apply a very strong electric field. In this condition, it is much more probable to get an ionization of the system just by using the electric field. Okay, and this is what is done during the discharge in the laboratories, okay, in the discharge tubes. Then we just make a very dilute gas at very low pressure, and then we just apply some electric field over there, okay. Now once the electric field is applied like this, and this particle, let's say, is ionized in some plus and minus, so this minus will be attracted towards this and the plus will be attracted towards this, right? Okay, so due to this electric field there should be a current. So as you can easily see that the original electric field was this, and so the plus will now be so the plus charges will be accumulating here and the negative charges will be accumulating here. So as a result, in this plasma there can be a current from plus to minus, right? So this current will be actually opposing the original electric field, okay. Now whenever we are talking about this type of system, we have to also remember, or rather keep in mind, that whenever we are talking about giving the energy, so basically here the electric field is giving the energy for the ionization, here the thermal energy. So when electric field is applied and some ionization is just caused by this, then you see after the ionization, the charged particles, they have very well directed motion, they know where to go. But if the system is ionized just by using thermal energy, then the system does not know where to go after ionization. So it's a random process because thermal energy does not care, right? It just leads to random motion. So this type of motion, which is led by the thermal energy, leads to random motion and is called a diffusion type of motion, and will be led by the concentration gradient. So whenever you have the dominance of thermal energy type of thermal energy, then what happens, the system will the particles will move to from a region of higher concentration or higher density to a region of lower density, as simple as that. So that is somehow you can see you can say as the rough symbolic direction for the thermal energy. But for electric field, this is even simpler. That will just, the particles will exactly move, okay, the particles will exactly move to the opposite to the external electric field, right? That's why, so the external electric field is like that, and the positive particle is just going, so external electric field is just like that, and the positive particles are going in this direction. So after some time, so there will be a concentration, and these positive particles will create a current which will be in the opposite direction, right? Okay, so that is something also to understand that, and of course, so I mean, once again, so whenever they, okay, maybe if this part is a bit confusing, just I am repeating that whenever some electric field is applied, first after ionization, the positive particles will follow the electric field. There is no problem for that. So they will follow the electric field, and the negative particles will just move to the opposite of the electric field. But once they are accumulated here and they are accumulated here, then only inside the plasma or the system you will have a current which will counterpose, or which will oppose the external magnetic electric field. Okay. So this type of directive motion under an electric field is known as drift motion. So in a plasma, always we can see there is a competition between drift motion versus diffusion motion. Okay. Now, just a bit of history. Okay. So that, I mean, you can also have the idea that, I mean, how important plasma is. So first of all, 99% of the whole known matter, not only in the universe, I mean not only in the astrophysical domain, but the whole known matter, the 99% of that is plasma. Okay. Now the plasma was introduced for the first time in the year 1929 by Tonks and Langmuir. Okay. So these two persons, for the first time, they use the word plasma. Okay. Now we have defined the formal definition of plasma. I mean, we have discussed the formal definition of plasma, and we have also seen that depending on the energy, okay, which is creating the plasma, we can have either diffusion or drift type of motion, but in a practical case you can have both, and then there will be a competition between drift and diffusion. Okay. Now now the next question is simply that what are the essential features of a plasma? Okay, so as I just said that plasma, first of all, plasma is an ionized medium, right? So we all agree that plasma is not a neutral medium. It is ionized medium, but it can contain ions, electrons. Ions means in the very complicated case it can also contain negative ions as well, and neutral. Okay. Now second thing is that plasma is globally quasi-neutral. Now there are 2 points. One is globally, one is quasi-neutral. What is the meaning of that? So first of all, globally simply means that the quasi-neutral properties or quasi-neutrality is not a property which is true at every point in a plasma. Okay. So you can simply now see the plasma as like a kinetic ensemble, but not like kinetic ensemble of neutral gas molecules, but a kinetic ensemble of charged particles, okay, ions and electrons. Okay, you can simply see that. Okay, as we will see that after certain conditions, plasma can also be treated as a fluid, but for the time being, you just see as a kinetic ensemble. Okay, so at every single point, or in the if you just take a local neighborhood of if you just take a neighborhood of any particle, any plasma particle in a plasma, then the question is that in this neighborhood whether the total charge density is zero or not. The answer is not necessarily. Okay, but if you take sufficiently bigger volume, okay, so then you can have actually globally quasi-neutrality. That means if you now take a sufficient amount of bulk of this material and then you just measure the charge neutrality, the charge neutrality will be almost zero. It is not exactly zero but almost zero. Okay, so and that's why this word quasi comes in. So globally simply means that you have to take into account the like some considerable amount of material or considerable volume, okay, with which if you just average, then the, or if you just take the total quasi neutrality, then so for example, if you just take this volume and then you calculate the total number of ions inside it and electrons inside it, and then you just add them together just to check the charge neutrality, okay, and charge density, you will see that that should be very near, close to zero. Okay, so that is the meaning of globally quasi neutral. Okay, now this globally quasi-neutral simply means that we have to define a length scale and a time scale beyond which the quasi-neutrality is defined. So, and for plasma, this is exactly the case. That is, globally means beyond one length scale and also beyond one time scale. Now this length scale is known as the, if you know, d by length, we denote by lambda d, okay, and the time scale is known by 1 by omega p, where omega p is the plasma frequency. Now you can ask me what is plasma frequency. That we will discuss in a few minutes. Okay, but before that, just to understand that what is happening, for example, so if you have one length scale, let's say this, okay, and then if you just take particles within this length scale, let's say if you take any volume, let's say this or this or this, well, you cannot expect charge neutrality. But if you take a volume of the order or larger than this scale, then you can simply expect that there will be a very negligibly small charge density. Okay. Now, and this length scale is known as d by length. Now, the how d by length is conceptually introduced in other way. That is that whenever in a plasma, now you go to this original picture. This is quite useful. Now, in a plasma, when you have this type of this type of charged particle like this, okay, then it is true that at the first look you can have this idea that maybe this plus will be recombined with, this plus will be recombined with this minus, or this plus can also recombine with this plus can go to this plus can go to this plus can go to this, like this. Okay, but is it really as simple as that? What happens, let's say, if your system just contains one positive ion and one negative ion, and then of course the only force which is acting between them is the Coulombic attraction force, right? But if the force is hindered by another negative ion, let's say, then what happens? These and these will act by a stronger Coulombic attraction force because this is closer to this, okay, and this one will be a bit farther. Then what happens? As a result, this one, when this will, as a result, when, just a minute, yeah, when this will try to come to this particle, after just coming the neighborhood of this particle, besides experiencing the attractive force due to this, it will also experience, actually it will experience from the beginning, but what I am saying that when it comes to the neighborhood of this particle, that then it is experiencing attractive force due to this towards this particle, but at the same time it is also experiencing repulsive force due to this particle. Okay, so attractive force towards this particle, repulsive force towards this particle. So that's why after coming to this particle actually may deviate, or I don't know, like may deviate like this. Okay, so what we actually assume that this coming from this point to this point will be very simple. Now in the presence of this third particle is no longer that simple, and this situation becomes worse if your system is having, let's say, some positive ions, and in practice the positive ions are bulky, so they are mostly the ions. Okay, so they are not protons, they are ions. And negative species, they are the electrons, they are very, very light. So okay, they are very, very light, so they can move anywhere they want. And finally you can always see that usually around every single ion, positive ion, you can have a cloud of negative ions. So a positive ion, okay, is surrounded by a number of negative ions. So it is actually screened by this negative ions, by the group of these negative ions. Not negative ions, the group of these electrons, not negative ions, electrons. Now let's say one electron which is coming towards this position, okay, before it could have been attracted by this plus directly, but now due to this cloud, when this particle is now here, it will be repelled because of the repelling force, and that's why this particle will maybe in practice would never reach this in the neighborhood of this particle. Okay, so then with respect to this electron, the ion is simply screened, and the characteristic distance of the screen is known as the Debye length. Okay, so I mean there are some analytical theory by which you can have some definitions of Debye length. So simply just by saying that in general, if there is a positive ion and a negative ion, the Coulombic force is like Q1. So when the particle so if this has a charge Q1 and this has E, so it will be Q1 E by 4 pi epsilon 0 r square, right? But if this particle is this positive charge is screened by a number of electrons, then with respect to another electron which is coming from far, okay, it will see this it will see the effective charge, not q but q times e to the power, that is exponential r by lambda d, okay, with a minus sign, and this lambda d is the Debye length. Okay, now in general for a for Debye length we have some expression, and for a plasma whose temperature is T, of course this is a kinetic ensemble, I told you we can assume that, so it can have a kinetic temperature. So lambda d is nothing but root over epsilon 0 is the free space permittivity, Boltzmann constant, and T the temperature of the plasma by n E square. N is the number density of the species. Okay, so just to tell you, when I say that T is the temperature of plasma, this is a wrong statement. This is actually the temperature of the species. So lambda d is corresponding to a species. For example, here when we are talking about the lambda d, it was the lambda d of the ions. Now the same type of thing can happen. So when you have a large collection of plus and minus, a minus electron can also be surrounded by very slowly moving ions, positive ions. Then some positively moving ion would also feel, although they don't move much, but anyways, if they move at all, okay, then they can also see some screening effect, okay, and thereby defining an equivalent lambda d for the electrons as well. Okay, so and n is the number density of the species. For example, here for the ions, so we in general write lambda di ti ni. E square is the charge square. So I mean we are talking in general in terms of the singly charged ions, singly charged ions and electrons. So charge is plus or minus E, so E square that will not change, and N is the number density of the ions. Okay, now you see that within the within the Debye length, okay, the charge neutrality is not valid. So that means Ni is not equal to Ne. Okay. Of course, if we are just talking about plus and minus charge, then if Ni so the total charge density at a point will be Ni times plus E plus Ne times minus E. So it will simply be giving you, if it is almost equal to 0, okay, then it will simply lead to Ni is equal to Ne. Okay, so for this type of specific systems, okay, the equivalent condition of quasi-neutrality can be written as Ni is equal to Ne. Okay, but the fundamental condition is this: the total charge density is 0 at every point. So Ni is equal to Ne is no longer true, but at d by length or beyond d by length, Ni is equal to Ne. Okay, so now we can do a very simple thing, that what is then the lambda d for what is the lambda d for ions? That is simply epsilon 0 kb ti by ni square. And what will be the lambda d for the electrons? That will be simply epsilon 0 kb te by ne square. Now let's say we just assume that Ni somehow is very close to Ne. Then lambda di by lambda de will be what? Will simply be Ti by Te with a root over. So if in a plasma the ion temperature is greater than the electron temperature, then the d by length, ionic d by length, will be greater than the electronic d by length, right? And if the ionic temperature is less than the electronic temperature, then ionic d by length will be less than the electronic d by length. Okay, this situation is known as hot plasma. I have to write it in red so that you can see it. Hot plasmas. Mostly the plasmas which are strongly ionized, that means the degree of ionization is very high, let's say 80% or 90%, then this is then for those plasma this type of condition is verified, and this is called a hot plasma. A plasma whose degree of ionization is very weak, then the electronic temperature is much greater than the ionic temperature, which is of the same order or a bit greater than the ambient temperature, and that is the case for the cold plasmas. So the thumb rule is that, so Te is always hot. I mean the electrons are more or less always hot, but if your ions are hotter than the electrons, then you have a hot plasma. If your ions are colder than the electron, then this is cold plasma. So mostly the laboratory plasmas, they are the cold plasmas, and fusion plasma, for example our space plasma, okay, they are fusion plasma, they are the examples of hot plasmas. Okay, another, so like d by length, we have another associated concept. This is the concept of plasma frequency. So as I just said, the quasi neutrality is guaranteed beyond one time scale and one length scale. So now let's say the time scale, so let's say the time scale is such that if the I mean if in a system you have sorry, you have positive ions and negative electrons. Okay, I mean not so beautifully like that, but anyways it's just I mean, yeah, okay, I'm making it full of positive and negative spaces. Okay, so now in general the total positive charge is almost equal to the total negative charge if you take a bulk. Okay, now let's say by some artificial way we just perturb that charge neutrality. Then the plasma will respond to such a fashion that its quasi-neutrality will be retained in a time which is 1 by omega p. Okay, actually not 1 by omega p but 2 pi by omega p. 1 by omega p is not the correct way of writing. 2 by omega p or 1 by fp. So this is known as the this f is known as the plasma frequency, although in very many literatures you can see omega p, which is the angular frequency, is known as the plasma frequency or is called the plasma frequency. No problem for that. And this omega is also defined for every single species. So if it is for the ions, that means if you just perturb the ion charge from, so let's say your original system has Ni is equal to Ne, and if you perturb Ni to Ni plus delta Ni, then the charge neutrality will be re-established with a time which is of the order almost equal to 2 pi by omega pi, where omega pi is nothing but root over n square by m epsilon 0. Once again, this will be Ni and Mi. E is the charge square, Ni is the number density for the ions, Mi is the mass of one ion, and epsilon 0 is the free space permittivity. Okay. Similarly, omega pe is nothing but root over Ne square by Me epsilon 0. Now, if you just want to compare those two, so omega, if I simply write this now, so omega pi is to omega pe will be simply equal to, again Ni is almost equal to Ne, so it will be simply equal to root over Me root over Mi. As mass of one electron is much more smaller than the mass of one ion, then the ionic ionic plasma frequency is lower than the electronic plasma frequency. That means if you perturb the electronic charge, okay, and the ionic charge by the same amount, the ion population will take much more time to re-establish its charge neutrality once again. Okay, but you see that unlike the Debye length, here the omega pi and omega p, their corresponding weightage, their respective weightage, that does not depend on the nature of the plasma, whether the plasma is hot or cold, right? That is something very, very interesting thing. So just for your for your convenience, so in the exams we will ask you to calculate this type of quantities. Okay, so we can supply you all the necessary quantities, and then we can calculate, you can calculate the plasma frequency, the Debye length, this type of thing. Okay, so this lecture was principally to give you a very short and level 0 introduction to the plasmas. So in the next lecture we will discuss the fluid picture of plasma. So plasma is a vast subject and it can equivalently be treated, it can be treated, well, not equivalently, okay, depending on the situation, it can be treated as kinetic ensembles. Sometimes it can be treated in as such an ensemble where the particle properties are, individual particle properties are very important. Okay, and for example, there is a phenomena called Landau damping, okay, where individual particle effect is very, very important. Okay, you cannot avoid that, and in certain situations it is only the collective effect which is necessary. So that I will tell you in the next lecture. Some people include collective behavior in the definition or characteristics of plasma. I will come to that in the next lecture, where I will first start by saying the standard 3 plasma criterion. Okay, thank you very much.